Start over. So today we are going to look at laws of logarithms and how they relate to exponent laws. Okay, so the first one is the product law. In exponents, if we have like bases and we're multiplying, we end up adding those powers together. So for logs, if we have the log of something multiplied, like we had bases multiplied, then that splits into two separate logs that are added together, just like the powers added together. Okay, so bases of exponents that are multiplied, a log of factors that are multiplied. We add the exponents, we add the individual logs. Okay, same thing works if we're doing natural log. Natural log of two things multiplied becomes two natural logs added. Okay, does that make a little sense there? So for quotients, dividing, if we're dividing with exponents, we have like bases, we subtract those powers. So if we have the log of a division, we will subtract those individual logs. Okay, same thing with natural log. If we have natural log of a division, then we'll split that into two natural logs subtracted. Okay, exponent rules, when dividing bases, the powers subtract. So in a log of a division, subtract the individual logs. That goes for log or a natural log. We good? Okay, power law. Power law. If we have a power, a to the n power, raised to another power, we multiply those. That's a power to a power. So we multiply those exponents. Okay, when you're taking the log of a base to a power, that power becomes a multiplier, but it becomes a multiplier out front, like a coefficient. It is a coefficient. Okay, so when you have the log of a something to a power, that power comes out in front. Okay, same thing with natural log. Natural log of x to a power, that power comes out front, and we have p times natural log of x. Okay, any general questions? Sorry. Any general questions on those log powers? All right, so last time we learned to drop and cross to convert from exponent form to log form, or backwards from log form to exponent form. Okay, so some of these special properties here are based on that drop and cross idea. Okay, so if we look here, log base b of b to a power. Okay, if we drop and cross, we'll have b, the base drops of the unknown, equal to what we took the log of, b to the x. Well, looking at this, the number in the box has to be x, so that's x. Okay, log base b of b to the power of x is simply x. Okay, similar idea with natural log. Remember, natural log is log base e. We're taking the log base e, or natural log, of e to some power. So dropping and crossing, the base e drops to the unknown power in the blank, equal to the thing we took the natural log of, e to the x. Okay, that box is x. So natural log of e to the x power is simply x. Okay, so a log of a base and a base of a power will undo each other. Log base b undoes b to a power of x and leaves you with just x. Natural log of e to a power, natural log and e undo each other, and we're left with the x. Good here? All right, same thing works with exponent form. B to the power of log base B of X. If we drop and cross, this B gets dropped as the base. Log base B of some unknown is equal to what that power was, log base B of X. Well, just looking at this, log base B of something equals log base B of X, that's X. Okay, so again, B as the base of an exponent and log base B undo each other and leave us just with that X. Same thing for E and natural log. E to the power of natural log. E and natural log will undo each other, leaving us with just the X. Okay? E and natural log will undo each other, leaving us with the X. Good? All right, now a couple others. Taking the log or the natural log of 1. Log base B of 1. Drop and cross. Drop the B to some unknown power has to equal 1. And that's for all cases of B. So the only way to guarantee we get 1 as the result is if 0 is the power. So B to the power of 0 is 1, making log base B of 1 equal to 0. Okay? Same thing happens with natural log. It's base E. So E to some power would have to be 1. E, remember, is a number, approximately 2.718. So that number to a power must equal 1. That power has to be 0. Okay? All right, any questions on any of these other properties here? We doing okay? All right, so let's go on to try a couple. Okay, there's a change of base formula. We talked about this just a little bit last time. To convert into a different base. This is mostly useful when you're trying to do this on a calculator that will only let you do base 10 or do natural log, so base E. Okay, it's very helpful if you have to do one or the other. So log base A, any base of X, can be converted into log of X over log of A. Okay, tell me what that base is if there's not one printed. There's not a base printed. What is that base? Yes, quite a few 10s in the chat. This would be log base 10. Okay, log base 10 if there's not a base present. Okay, now same thing, we can do the same thing with natural logs. Log base A of X equals natural log of X over natural log of A. What's the base of natural log? It is base E, and that is a lowercase e. Okay, now what my brain remembers, okay, how my brain remembers this, which one goes where, is that the base goes to the bottom. The base goes to the bottom. Okay, the base is the bottom of these fractions. Okay, we good? All right. Stop that for a minute. So to evaluate using those log rules, okay, to evaluate using those log rules, we want to apply those properties on the first page, those properties of logs, and we want to try to get there's a couple different types of problems. okay? We want to try to get this as simplified as possible. When this says evaluate, that means the answer we're looking for is a number. It's the number that expression is equivalent to. Okay, so part A says log base 4 of 16 to the power of 6. Okay, from our properties, from those properties, this power of 6 comes out to be a multiplier. So we have 6 times log base 4 of 16. Okay, now we need to find log base 4 of 16. Okay, so come off here to the side, drop and cross. Convert that into its other form. Log base 4 of 16 would be drop the base of 4 to some power equals 16. Well, 4 to what power is 16? 2. So log base 4 of 16 is equal to 2. We had the 6 that was the power that came out as a coefficient, and 6 times 2 is 12. Okay, so log base 4 of 16 to the power of 6 is 12. Okay, questions on where that came from? I'm not seeing or hearing anything. Okay, so on part B, e to the power of natural log 50 plus natural log 2. First thing we want to do is condense this into a single log. So we have 2 logs that are added, 2 separate logs that are added. Think adding 2 exponents. That means the bases had been multiplied. So we're going to multiply those values 50 times 2. Okay, to condense 2 logs that are added together, take 1 log and multiply those values. So now our exponent is natural log of 50 times 2. So then that's e to the natural log of 100. Okay, from those special properties, e and natural log undo each other. So e to the natural log of 100 simply becomes 100. Okay, questions here? All right, let's look at example 2. Okay, this is a common type of question that you'll see. Okay, this also tends to come up on ACT tests a lot, so this can be useful to you. Okay, we're asked to express this as multiple logs. It may also be, you may also be instructed to expand this. Okay, now when this is completely expanded, okay, when these are completely expanded, inside each log function, you will have a single value. Okay, a single value inside each log function. Okay, as in no powers, no other terms, no other anythings. Okay, so when you're asked to express in the following in multiple logs, okay, each log term, each log term is of a single value. Okay, no powers or operations. Okay, no powers or operations, as in no 3 times 4s, no x to the 5th powers. Okay, each log taken is of a single value. Okay, so we're looking at example A. and we are multiplying all these things inside a log. Okay, think multiplying bases with exponents. If you're multiplying bases with exponents, we add the powers. So here we're multiplying multiple factors inside a log. So when we split those up, they're added. Okay, so log base A of x squared, then a plus sign, then a new log base A of y to the third, then a plus sign, then a new log base A of z to the power 5. Okay, we split those into the sum of individual logs. Okay, now each log term needs to have no powers inside it. Okay, so that other log law says that if you have the log of something to a power, that power comes out as a coefficient. So log base A of x squared, this square comes out as a coefficient, and we get 2 times log base A of x. Now we have just a single x inside that log. Same thing with the second term. This third power inside the log comes out as a coefficient, and we have 3 times log base A of y. Good? All right, then on the last one, this power of 5 comes out front, and we have 5 times log base A of z. Good? All right, take a peek at that for just a second. Ask questions if you have them. So on part B, natural log of x, y squared over z to the third. We have x multiplied by y squared, but then that's divided by z to the third. So the natural log of x and the natural log of y squared will be added because x and y squared were being multiplied inside the log. Then z to the third is being divided, so it will be minus natural log of z to the third. Okay? The plus sign is because the x and the y squared are being multiplied. Okay? 2 factors that are multiplied inside a log, split into 2 separate logs added. Then a division would be a subtraction. Okay? Then we do the same idea with the coefficients. This first natural log doesn't have one, plus this 2, this squared on the y, comes out in front and becomes a coefficient. Okay, minus the natural log z to the third, the 3 on the z comes out as a coefficient. Okay, so this whole thing at the bottom, these 3 terms, 2 added and then the third subtracted, are your final answer here. Okay, any questions on this? All right, so going on to example 3. Okay, going on to example 3. Express as a single log. So what we're looking for here is log of one big thing. Okay, we want everything condensed into one single log. Okay, so this is like a working backwards thing. Okay, so to express these as a single log, first thing we need to do is take any coefficients we have and turn those back into exponents. So this 2/3 coefficient in front of natural log of x becomes natural log of x to the power of 2/3. Then this 1/2 natural log y, that 1/2 becomes the power on the y. Good? So we'll have natural log of x to the 2/3 minus natural log of y to the 1/2. Now, that's two separate logs being subtracted. Subtracted leads to division. So then this becomes natural log of these two factors divided. X to the power of 2/3, y to the power of 1/2 in the denominator. Okay? Anything else? Any questions? With these being different variables, an x and a y, we can't simplify those any further. So we will just leave it like this. Okay. Had there been different powers of x involved, we would use the regular exponent rules to simplify this as far as possible. Okay. With these being different variables, we can leave one of each variable. We can't leave multiple of any variable. All right, on part B, we're going to do the same thing. We want to take all three of those terms, condense them into the log of one big thing. So take this half, it becomes an exponent. So now it's log base A of x to the 1/2. Take this 3 coefficient, it pops up as the exponent. So it's log base A of y to the 3rd. Then minus this 2 pops up and becomes the coefficient, log base A of z squared. Okay? Now, we have two of these terms added and the third term subtracted. So the two individual logs that were added together condense into one log of the two factors multiplied. So log base A of x to the 1/2 times y to the 3rd, because these two individual logs were added. Okay, this third log was subtracted, so it's log base A of z squared being subtracted, so that z squared ends up divided inside our single log. Okay, so we have x squared in our denominator. Are we good? Any questions here? All right, we're gonna take a 5-minute break. So on these quick examples, on number 1, we want to condense these three terms into a single log. Okay, we want to condense those into a single log. We've got a mix of adding and subtracting, so we're going to have a fraction. Okay, is the log of A being positive, that A is going to go in the numerator. Okay, log of B squared, where is that B? Where is the B squared going, top or bottom? Yes, good, because it's being subtracted, because that log is being subtracted, that B to the 2nd factor goes in the denominator. Sorry, 2's are messy on this thing. Okay, then log of C to the 1/3 power, is that C to the 1/3 going numerator or denominator, top or bottom? And yes, this is going to go in the numerator because it is positive, it is being added. Okay, so it is multiplied inside that single log. Okay, so we'll have log of A times C to the 1/3 all divided by B squared. Okay, questions here? All right, then on this second one, we are expanding this into individual logs, okay? We have the log of f to the third, g to the fourth, over h. So that's going to be 3 separate logs, okay? We'll have the log of an f to the third. We'll have a log of, we'll have a log of g to the power 4. Okay, then we'll have a log of h. Okay, now for some signage between log of f to the third and log of g to the fourth, what sign do we need? Is that going to be a plus or a minus? This is going to be a plus, okay, because f to the third and g to the fourth were multiplied inside the single log. So when we expand them to separate logs, they get added. Okay, then log of h, is that going to be added or subtracted? What symbol needs to go here? Yes, that's a subtract because the h was being divided inside a single log, so it will be subtracted in our expanded logs. Okay, now what? Are we done with this yet? No. Okay, we are not done with this yet because to expand, each log needs to contain a single value. No powers, no operations, no coefficients. It needs to contain one single value. It can be a double-digit number, but it could only be that number, not that number to a power, not that number with any other thing done to it. Okay, so what happens to those exponents? These exponents become what? These exponents become coefficients, okay? So this third power becomes a 3 multiplied in front, okay? Let's see if I can erase just that 3. Maybe, hey, not bad. All right, that's supposed to be going. All right, this 4 on g to the power of 4, that 4 becomes the coefficient in front of that log. So 4 times log of g. Okay, we don't have to do anything with this h because it was already just a single h. So this whole expression right here, not bad, this whole expression right here is our final answer. It takes a little bit of room. Okay, any questions on these? All right, then we're going to look at a related but slightly different part of this lesson today, and that's going to be using these log properties and using this condensing and expanding in order to solve. Okay, now this is a type of question, this example that's worked out right here. This is a type of question that comes up a lot on SATs. Okay, we want to solve this, and we're solving this by hand, as in with not using a calculator. Okay, so we have 25 to 1 power with a variable equaling 1/5 to another power but with the same variable. Okay, to solve equations where the variable is an exponent, the values on both sides of the equation need to have the same base. So we're going to convert 25 and 1/5 into the same base. This is where knowing those perfects that we keep talking about, that little quiz over next time, it's going to come in handy. Okay, in this case, the base we can convert both of these into is 5. Okay, 25 is 5 squared. We didn't change anything. We just wrote 25 down as 5 squared. Same thing with 1 over 5. That's 5 to the negative 1 power. We haven't changed anything. Okay, we haven't changed anything. What do you think equals? We've just rewritten 1/5 as 5 to the negative 1 power. Okay, now we have a power to a power on both sides. So when we have a power to a power, we multiply. So 5 to the power of 2 times x minus 3. On the other side, 5 to the power of negative 1 multiplied by 4 minus x. Okay, then multiply the exponents, distribute. So 2x minus 6 and negative 4 plus x. Okay, now this is written wrong and I edited this like 3 times. Okay, so on both sides now have the same base. Okay, both sides now have the same base. Okay, both sides have the same base, is what that is supposed to say. Okay, both sides have the same base. What we can do with this now is make the exponents equal to each other. I got a little overzealous there. Okay, both sides have the same base, then the exponents have to be equal to each other. Okay, so what we're talking about here is now that we have 5 to a power, 2x minus 6, and 5 to another power, 4 minus x, those two powers have to be equal to each other for this statement to be true. Is that reasonable? So take the two exponents, set them equal to each other, and solve like you would any equation. 2x minus 6 equals negative 4 plus x. Move your terms over. X equals 2. Okay? Any questions on that? Okay, you can check this, okay, by plugging into the original problem, 25 to the x minus 3. So that's 25 to the 2 minus 3, or 25 to the negative 1, which is 1 over 25. Then 1/5 to the power of 4 minus x. So 1/5 to the 4 minus 2, or 1/5 squared, which is 1 over 25 as well. Okay, any questions on how that worked? Anybody seen these on SATs or ACTs like this? Yeah, convert to the same base, and then you can do what you need to on the exponents. Okay, now there's quite a few different types of problems that can come up. Okay, if you have a base to a power on each side, you want to make those bases equal. If you don't have a base to a power on each side, you want to use probably the drop and cross idea. Okay, so here, drop and cross. X to the power 4 is 625. Drop the base, the 4 and the 625 crisscross. Okay, now officially what we're doing here is taking the 4th root of 625. If you've been working on those perfects, you know that 5 to the power of 4 is what gets you 625. So x here is 5. Okay. On part C, we have a coefficient in front of a log. That coefficient in front of a log pops up to become a power. So now we have log base 4 of x equal to log base 4 of 3 to the 3rd. Well, 3 to the 3rd is 27. So now log base 4 of x is equal to log base 4 of 27. Okay, so x has to equal 27. In this case, instead of getting the bases the same, the base of the logs were already the same. We just needed to condense and simplify each side into one single log. Okay, any questions on that? All right, so on part D, we only have a log, so we're going to drop and cross. Okay, drop the base of 8, cross the x in the 32. So x to the power of 8 is 32. Well, x to a whole number power is not going to give us 32. So this is one of those cases where we need to convert to the same base. That base is 2 because 8 and 32 are powers of 2. Okay, another reason to study those perfects. Another reason to study those perfects. Okay, so rewrite 8 as 2 to the power of 3. Rewrite 32 as 2 to the power of 5. Okay, then we'll have 2 to the 3x power, multiplying those exponents, power to a power, equaling 2 to the power of 5. Okay, just making those into the same base and simplifying each side. Okay, now we have the power of 3x has to be equal to 5. Those exponents have to be equal because we made the bases the same. For that equal sign to be true, the exponents have to be the same as well. Are we good? So then solving that, 3x equals 5, just divide by 3. Leave these in fraction form. Pardon me. Don't worry about decimals. Sorry, had to plug in. Okay, so leave this as 5 over 3. Do not make that a decimal. Do not even think about making that a mixed number. Leave that as 5 over 3. Okay, are we okay here? Any questions this far? All right, when you first look at question E, you're probably thinking, oh no, okay, it's not that bad, I promise. Okay, if you look at the right hand side, you see 3 individual logs. Okay, condense those into one single log because that's what we have on the left is one single log. Okay, so this coefficient of 3 makes this 2 to the 3rd power, which is 8. This coefficient of 2 makes this log of 3 to the 2nd. 3 to the 2nd is 9. This 1/2 power, got cut off, sorry. 1/2 power is 16 to the 1/2 power. We talked about last week 1/2 power being the same as the square root. So 16 to the 1/2 power is the square root of 16, which is 4. Are we okay to this point? Now, condense this into one single log. The log of 8 is added to the log of 9. So when we condense that into one log, it's 8 times 9. Then we're subtracting the log of 4. So that 4 gets divided inside the single log. Okay. 8 times 9 over 4 is 18. So we have the log of x on the left that we've left alone till right now, but we brought him back now, equal to log of 18 that we simplified from all this mess up here. If log of x equals log of 18, the only thing x can equal is that 18. Okay? How are we doing on these? Questions? All right, so just a handful more. Yeah, just a handful more on this last page. Okay, we want to simplify and evaluate or find x. Okay, so in the case of something like in the case of something like A, we want to find out what this equals. We want to get a numeric value for this as simplified as possible. Okay, so we have two individual logs being subtracted. We want to condense those into a single log. So log base 5 of 14 minus log base 5 of 2 condenses to log base 5 of 14 over 2. 14 over 2 is 7. So we have log base 5 of 7 as our exponent. This was 5 to the power of log base 5 of 7. And like we talked about in those log properties in the first part of this lesson, this 5 to the power of and this log base 5 undo each other and leave us with just this 7. Are we okay there? Condense the log, then 5 to the power of and log base 5 will undo each other and leave us with just this 7. Okay, questions here? All right, on B, we have 8 to the power of log base 2 of 6. We don't have an equal sign. We're not equating this to something else, but we have a base of an exponent that's an 8 and a base of a log that's 2. We want those bases to be the same, even though they're not on two separate sides of the equation. Okay, we want the base of the exponent to match the base of the log. Okay, so we can rewrite 8 as a base of 2. So 8 gets rewritten as 2 to the third to the power of log base 2 of 6. Then using exponent rules, raising a power to a power, multiply 3 times log base 2 of 6 is now our exponent. Okay, then the 3 coefficient in front of the log comes up and becomes the power on the 6. So 2 to the power of log base 2 of 6 to the third. Okay, that's a lot. This 2 is the base of the whole problem. Log, this base is the 2 of 6 to the third. Good? Now, log base 2 and 2 to the power of undo each other. So we're left with 6 to the power of 3, which is 216. That is one of those perfects that you're going to need to know. Okay? Are we okay here? All right. Part B, C, I'm sorry, C. We have the log of something, we have a log of, a log of, a log of something. And that looks like a lot, okay? If you'll treat this just like a function inside a function inside a function, this will work, okay? So we want to work from the inside out. So we're working this log base 2 of 256 first, okay? So log base 2 of 256, we're going to call it x, and that's going to be what this innermost term is equal to. So log base 2 of 256 equals x, drop and cross. Drop the base of 2, cross the power of x, cross equals 256. Drop and cross. Okay? Now, it's good to know lots of powers of 2. 2 to the 8th is what equals 256. So x is 8. We okay this far? Okay, now we know that log base 2 of 256, all this stuff here, is 8. So now we're doing the next piece out. Log base 2 of this equaled 8. So log base 2 of the 8 we just found, and we're going to call it y. We need to call it a different letter because it is a different value. Okay, then we'll do the same thing. Drop and cross. Drop the base of 2, cross the power of y, cross equals 8. 2 to the power of y equals 8. Well, we know that 2 to the third is 8, so y is 3. Okay, now we know all this inside stuff that's underlined here in green, all this inside stuff is equal to 3. So we're going to start on the outside again, the next piece, which is the last one, log base 3 of whatever we got for all of this stuff, well, that's 3. Log base 3 of 3, and we're going to call it z. Again, a different variable because it's a different letter. It's a different value. Okay, drop and cross. 3 to the power of z equals 3. So z is 1. Okay, so the answer to all of this, log base 3 of log base 2 of log base 2 of 256 equals 1. You can groan and roll your eyes that it took that much work to get to the answer of 1. It's okay. We good? Any questions here? All right, so on D, okay, last one. We have 49 to a power with a variable equal to 343 to a power with a variable. This is a classic case of needing the bases to be equal. Okay, you have 2 different bases that have powers with variables. You want those bases to be the same in order to solve this. Okay, 49 is a power of 7, so is 343. So 7 squared to the 2x minus 1 equals 7 to the power of 3 to the x plus 1. Okay, raise a power to a power, so we multiply. 2 times 2x minus 1 gives us this 4x minus 2. Then 3 times x plus 1 gives us 7 to the 3x plus 3. Okay, now we have 7 to 1 power equaling 7 to another power. Those powers have to be equivalent. So 4x minus 2 is equal to 3x plus 3. So x is 5. Okay, any questions on that one? Let me see that whole problem. You've been awfully quiet with the questions. Are we okay today? Okay, your practice is 2 parts. Okay, your practice is 2 parts. There is an AXL link that is your practice on part A of this lesson. That was the laws of logs. Okay, you have a Google form that is your part B practice, which is solving these equations. Okay, highly recommend you work all those out step by step by step. Okay, you're definitely going to want scratch paper as you work those. Okay, on that form, there's somewhere you're typing in the answer. When you type in the answer, type in just the number. So if question D was on the form, the only thing you type in for that answer is 5. We good? Just the numeric values.